Good afternoon. My name is Thomas Down, and I'm going to be doing Learning Module 4, I/O and subroutines, and time delay routines. With the PIC microcontroller, like any other microcontroller, you have the ability to use macros, subroutines, and then read and write to input and output pins. A macro, when we get down here, a macro is a set of instructions that's used by the assembler, and it turns it into actual PIC microcontroller instructions. And every time that the macro is found within a .asm file, it's turned into the actual instructions or coding that you need. And unlike a subroutine, every place that the macro is found, it's inserted into the actual program, so it can lengthen the program significantly. Subroutines, on the other hand, are pieces of software that you use repeatedly. And typically what you do, you have only one instance of the subroutine in your program, but then you can call it anywhere you need to from your inside your program, and it will execute the subroutine. There's some things that you've got to be aware of. Since you're calling a subroutine, the program counter is actually going to jump to the address location of the subroutine. When it does that, it needs to know where it's coming back to. Inside here we have something called a stack. A stack is a temporary location where we store addresses and data. A stack, one of the analogies we use for a stack is similar to what you might find in a cafeteria, where you have, when you walk up and pick up a plate, well, you can put a load of plates onto it, and the plate that's on the top is the first one that comes out. Stacks are similar to that, but they're memory, and you put addresses and data on the stack if you want to recall them later. So when we call a subroutine, it can be put in the program before the start instruction, or the start start label, and then you can put them after the go to $sign label. So they're really outside of the program, but they can be called from within the program. So if you are executing your program file and it comes into a call subroutine, it then takes the stack and pushes it onto the program counter onto the stack, and it executes your subroutine. Once the subroutine is finished, the subroutine needs to tell the microcontroller that it's done. So there are two instructions that tell it that. You can either use a return, and we refer to that as return from subroutine, or we have the RETLW. And the return with literal in the W register is a unique instruction for the PIC microcontroller. That way, if inside the subroutine you're operating on a piece of data, and you need that external to the subroutine back in your main program, like a global variable, then you can return with that literal. And that's a very useful feature. Here we have a very simplified block diagram of, we have our main program, and as our microcontroller is operating, come in through our main program. We're executing down this way through our main program. All of a sudden we see a call subroutine instruction. The program counter is for the program is put on the stack. It goes to the subroutine, comes over here and executes the subroutine, jumps into it. Once it finishes executing the subroutine, it runs into either the return or the return with literal in the W register. It pulls the address immediately following the address where the call was out of the stack and starts executing the program again. Subroutines are common in almost every programming language, nothing unique there. Another thing that can be done in programming is a subroutine within a subroutine. We refer to that as a nested subroutine. This document's a little messy, but it depicts calling a program. A main program file is running. It calls a subroutine. It sticks the address on the stack where it needs to come back from in the main program. Within a subroutine, it calls a second subroutine. When that subroutine is actually executing, it can call another subroutine. This diagram depicts 3 subroutines being called from a main program, one after the other, and they're called nested. The way I like thinking about it, if you've seen the little Russian nesting dolls, well, one doll is inside the next doll, inside the next doll. Same thing here. You have 3 subroutines and the main program. And when you execute the first subroutine, it can call another subroutine, and then the next one can call the third one. Some cautions, some things to be aware of. If you call too many subroutines, depending on the particular microcontroller you're using, which PIC you're using, some of them have a limited number of subroutines that you can call. If you call too many, what you end up doing is you overwrite the stack and the program can crash. 3's not too many in most cases, but you have to be careful not to call too many subroutines in a nested format. Now, why would we use a subroutine? Well, with the subroutine, we can do several different things. If we have a repeated piece of code that we need to use over and over again, we can do that. Or one of the ones that we're going to come up on here in the next page is timing routines. A lot of things that we do require system timing or timing because of the fact that the microcontroller, the PIC microcontroller in this case, if it's operating at 20 megahertz, each instruction takes 4 clock cycles. So that means the instruction takes, it's 5 megahertz in frequency, but 0.2 microseconds in time to perform one instruction. That's very fast. People can't perceive that. I mean, you can't even imagine what 2 microseconds looks like. But in the PIC microcontroller, we need to be able to determine how long an instruction operates and how long a segment of code or a section of code is. And one of the things we can do is create a delay routine. When you push a push button, typically it's 20 milliseconds or so when you push that button before the contacts inside that switch close and settle down and things like that. So you need to have some way to create a delay in the microcontroller that people can work with. If you push the button and if the microcontroller is going at 0.2 microseconds per instruction, it might never see you push a push button. So you have to slow it down. So a delay routine is one way to do that. But we also need to be able to calculate delay routines. So here we take 20 megahertz, we divide it by 4, we find out the instruction frequency is 5 megahertz, and then the instruction cycle, if you remember the equation, time is equal to 1 over frequency, and the frequency of 5 megahertz, so the reciprocal of 5 megahertz is 0.2 microseconds. That's really fast. Here we have an example piece of code. In our code segment here, we look at a delay loop. So we have what we're calling the one loop delay. We have an instruction that says move a literal to the W. In the W register, we're going to write the hex value 02, and then we're going to move the W register to a file register, which we have labeled temporary. It's just a memory location that we've set aside to hold data. Then we come into our loop here. Our loop has a decrement F, which is decrement file register, and we're going to decrement the temp register, which we put 02 in, and then we're going to store the value back in the file register. Then we're going to test it and bit test and see if it's 0. If it's not 0, we're going to go back and decrement F again, bit test it, and then if it's 0, we're going to come out of the loop. Well, here we go through this loop twice. So we have these two instructions here, to move literal to W and to move W to F to load our value we want to count down. Then we go through this loop 2 times. And then once we're done, we kick out of it and pass on through. So when we look here, we've got 1 cycle for the move literal to W. We've got 1 cycle to the move W to F. Then we have the decrement F, which is 1 cycle. We're going to bit test twice, and then we're going to loop twice. So each one of these instructions ends up being part of our loop cycle. And under temp 2, we have 1 instruction, 2 instructions, plus another one, plus 2. So we end up having a total of 7 cycles. Okay. Now, our overall cycle count includes 2 additional cycles, so we get a total of 9 cycles. 9 cycles, when we start looking at it, ends up being 9 cycles times 0.2 microseconds per cycle, or 1.8 microseconds, which is pretty precise timing. When we go to the simulator, we can actually simulate it and look at the time on the stopwatch. By doing that, we're able to predict the amount of time we have for our program and loop. Okay. Now, being able to time things, we want to put them out on a I/O pin, so we need to set up our I/O configuration. In our I/O configuration, we need to program the microcontroller's input-output pins. And what's unique about the input-output pins is we have an I/O port, and then we have an I/O register. And our I/O register is kind of like what we call a data direction register. It tells us whether we're going to have an input or an output. Here we show a simple transistor circuit with a LED connected to it. And how do we make things happen? Well, we have to set the port up. We tell a pin whether it's going to be an input port or an output port. We can read from the port input, and we can write out to it, and we can shift in there when we configure it. Here we talk about how to set up a subroutine. In preparing a subroutine, there's some important features, because when you call a subroutine, a lot of times you want to hold on to what's in the W register and in the status register, and we need to be able to do that. Our configuration word, the PIC microcontroller has a configuration word. In the config word, we tell it clocks, whether we're going to have a write enabled, watchdog timer enabled, those kind of things. are controlled there. Part of it is setting up whether we're going to use an oscillator or a resonator. The 877, our config word also has some additional bits that we can enable. PIC88 also has some additional words that we can use. With the PIC88 and the PIC16F877 and the PIC-16F84 alpha, we have a lot of features and power that can become available to the programmer. It takes a little bit of detailed time and instruction. Thank you for listening to my presentation, and have a good day.